A major accident hazard, or MAH, is a catastrophic release of toxic, reactive, or flammable chemicals. When a pressurized system breaches, the resulting kinetic expansion poses an immediate existential threat to human life and the surrounding infrastructure. To manage these specific threats, the federal government established OSHA Standard 1910.119, the Occupational Safety and Health Administration's regulatory framework for handling highly hazardous chemicals. The core requirement driving this entire federal framework is the Process Hazard Analysis, or PHA. A PHA is a systematic, ongoing engineering methodology used to identify, evaluate, and control these major accident hazards throughout the life of a facility. It is a living process built to evolve alongside the plant itself. A federal mandate written in Washington cannot physically stop a pressure vessel from rupturing. The actual prevention of a disaster relies entirely on how risk engineers operationalize this PHA protocol on the ground. Consider the massive scale of a multi-unit petrochemical plant with its thousands of miles of interconnected pressurized piping. Now compare that to a single uncrewed distribution terminal. Because industrial facilities operate on entirely different scales of complexity, there is no single universal method for conducting a process hazard analysis. This requires methodological calibration. Engineers must match their specific risk assessment tool to the exact complexity of the asset they are evaluating. We are going to examine how to map these methodologies, from HAZOP to LOPA, directly to asset complexity, utilizing multidisciplinary teams and rigorous risk matrices to quantify the threat. Applying the wrong tool to an asset wastes resources or leaves fatal blind spots. Mastering this calibration makes the difference between performing a meaningless paperwork exercise and building a genuine, life-saving safety architecture. Before a hazard analysis, OSHA mandates compiling complete process safety information. This means gathering precise data on toxicity, operating temperatures, and flow rates. These raw metrics must be synthesized into finalized piping and instrumentation diagrams, material balances, and relief system designs. With the documentation complete, the analysis requires a specific human element. OSHA enforces strict composition rules for the team executing the PHA. The group must be explicitly multidisciplinary. It requires members with deep expertise in theoretical engineering combined with those who handle daily process operations. Legally, the team must include at least one employee who possesses localized knowledge of the exact chemical process currently being evaluated. Additionally, one member must serve as the facilitator, acting as the resident expert in the specific PHA methodology being utilized. The most accurate engineering data is useless unless interpreted by a team holding both theoretical expertise and localized, hands-on operational reality. To categorize risk tools, we look at the technical maturity and overall complexity of the facility along a spectrum. At the low end of the spectrum, suited for simple logistics operations or highly mature processes, we find the what-if and checklist methodologies. These qualitative approaches provide sufficient risk evaluation by systematically asking what could go wrong without requiring complex calculations. Moving to the middle of the spectrum, where operations involve complex, interrelated chemical systems, facilities deploy a HAZOP. A hazard and operability study is a rigorous line-by-line engineering review of those finalized piping and instrumentation diagrams. The team applies guide words to the diagrams to search for operational deviations from the original design intent, like unexpected pressure spikes or flow reversals. At the extreme high end of the spectrum, dealing with highly volatile quantitative risk, the team steps up to LOPA and SIL analysis. Layer of protection analysis, or LOPA, and safety integrity level analysis, or SIL, are rigorous semi-quantitative and quantitative evaluation tools. These advanced calculations are reserved for analyzing specific safety instrumented functions, where a single failure could escalate directly to a catastrophic major accident hazard. Over-engineering the safety analysis of a simple facility wastes capital, but under-engineering the analysis of a complex facility guarantees an eventual catastrophe. Once the hazards are identified, the PHA team must standardize their findings, translating theoretical debate into strict operational data. This chart shows the standard risk evaluation architecture. To measure severity, the team consults the consequence table. A Class 4 event is defined as resulting in multiple injuries or fatalities. Next, they measure probability using the likelihood table. A likelihood class of 3 means the event is expected to occur several times during the life of the process. By combining these two metrics, the team maps the true risk level. Tracing the intersection of consequence 4 and likelihood 3 on the risk priority matrix lands exactly on priority level A. Consulting the legend shows what Class A dictates. This is an intolerable risk. It requires mitigation within 2 weeks or the immediate shutdown of the entire process. To downgrade this risk to a tolerable state, the facility must enact engineering controls, like automated shutoff valves, or administrative controls, like restricted operator access. Compare this to a Class D risk, which is deemed acceptable and requires no further action. This shows exactly how the matrix prioritizes capital allocation. The risk matrix forces corporate management to abandon subjective guessing and adhere to mathematically bounded safety deadlines. The moment a PHA is finalized, it begins to age. The physical reality of a facility instantly drifts from its engineering blueprints. Engineers call this creeping change. Tiny, necessary daily modifications accumulate over months and years, gradually warping the original safety design intent. Routine tweaks trigger a management of change protocol, feeding data back into the risk model. To combat creeping change, OSHA requires facilities to update PHAs every 5 years or maintain data continuously as an evergreen PHA. A static hazard analysis is inherently dangerous. Safety barriers only prevent disasters if they adapt to the current physical reality of the plant. A compliant process hazard analysis requires a rigid architecture, beginning with a clearly defined scope and an uncompromising standard for evaluation. It depends entirely on the deployment of a multidisciplinary team that wields highly localized knowledge of the facility. It demands calibrating the specific analytical technique to the exact complexity of the asset, and it requires continuous review and periodic updates to combat the physical entropy of creeping change. By integrating these facets, organizations stop treating OSHA 1910.119 as an administrative burden. They transform it into a living, operational shield against catastrophic failure.